Tampa Bay Buckeye, Houston, how does dark energy affect gravity around black holes? It doesn't. So what I did in my paper, and let's see if we can, and I try not to like have like calculus and differentials. There we go. We go there. We turn off. Oh, nope. Wrong thing. I want to just. There we go. Okay. So this is from the University of Hawaii Academic Journal, talking about how that stuff happens. So what I basically did was about 6 billion years ago is when we noticed when dark energy took over. And this is because I've described this before. Like, take a baseball, you throw it up in the air. There comes a point where the ball goes up, it stops from the pull of gravity, and starts accelerating back down again. One of the models of the universe was the Big Bang goes boom, everything expands outward, slows down, stops, and then falls back in on the center of gravity again. That was called the Big Crunch. And so what we saw was the universe went boom, everything expanded outwards, and it started slowing down, kind of coasting a bit, slowing down. Then there became a point about 6 billion years ago where it was no longer slowing down, it started speeding up and going faster and faster and faster. That's when dark energy took over. So what I did was I basically created a mathematical model where I took two galaxy clusters. And these are the largest objects that had been gravitationally bound, and about 6 billion years ago they became unbound from dark energy. These galaxy clusters, like, you know, Milky Way and Andromeda form a little galaxy cluster. There's like the Virgo cluster and other clusters of galaxies all over the place. And so right now you've got these galaxies that kind of orbit each other, and they are now separating from the others that orbit each other. So these galaxy clusters can be thought of as like the largest gravitationally bound objects in the universe. So I took two average galaxy clusters and put them at average distance from each other, which is about 30 million light years, 10 megaparsecs. And I calculated the strength of gravity between the two of them. And I assumed that at that moment, the strength of gravity between the two galaxy clusters and the strength of dark energy between the two of them equaled the same. And that gave me a constant for the power of dark energy. Because after that, when they drifted apart, gravity got so weak that dark energy got stronger, started pushing them further apart faster. So that was in my assumption, that was the moment that gravity equaled dark energy. And as you get further and further away from an object, gravity gets weaker. Gravity works as a 1 over r squared law, meaning whatever your radius is, you square it, and that's how much weaker that power has gotten. So if my glass of water is 1 meter from me, the power of the gravitational pull between me and the water is 1 over 1 squared. But if it's 2 meters from me, it's 1 over 2 squared. So it's 1/4 as powerful as it was when it was 1 meter from me. So the strength of gravity falls off very quickly over great distances. And the constant for gravity is pretty small. It's 10 to the negative 22. It's a tiny little thing. So you need a lot of mass to make gravity worthwhile. So anyway, I set up this mathematical model. I set the constants for it, and then I calculated where those galaxy clusters are today. So they were 10 million or 30 million light years apart then. Now they're, I can't remember what the number was, 40 something million apart today, 6 billion years later. And I calculated the strength of gravity between them. And I calculated with the constant I created for dark energy, the strength of dark energy. And what I got was 2.96 to 1. Basically, that dark energy is almost 3 times more powerful than gravity, which is exactly what we find when we're calculating it via other methods. So I'm like, okay, this works out pretty well. And there's a couple of theories about how much energy is created when these two objects, I'm getting ahead of myself. When matter and antimatter appear in the universe, there's some estimations as to how much energy they release and how much that is. And it's estimated to be about 10 to the negative 80th joules per cubic meter. Now, I don't know what 10 to negative 80th is. 10 to negative 80th is, let me just show you. Oops, I didn't do that. I want to do that. Calculator, there we go. Our old friend calculator. Okay, so it would be 0.0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It won't even let me do it. I can't even do it. I only get to 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. I can go 10 to the negative 16th on this thing. I don't think it has a scientific calculator button here. Oh, on standard scientific. Here we go. All right. So I want to do 10 to the negative 80th. So this guy. Super duper tiny. We're like approaching a negative googolplex. That's how tiny it is. But if it's a constant, and it's a constant for every cubic meter of space in an entire section of space that is 30 million light years across, that is a horrendous amount of volume. There's a lot of cubic meters inside of that. So you can then calculate that constant, that 10 to the negative 80th, across the entire thing, and it gets us to this 3 to 1 that we have in in my paper. So my paper, like, normally these theses are like 60 pages long, and I refused. I was like, no, I can do it in just a couple of pages. And my advisor was like, you better make it like 60 pages long. I said, no, I'm not. I'm gonna make it like 6 pages, and it's gonna be done. You know, Watson and Crick won the Nobel Prize for a 1.5-page paper on the discovery of DNA. I don't need to go 60 pages into this thing to describe this little 3 to 1 ratio. And he was like, I'm not going to let you graduate if you don't make it 60 pages. I handed this thing to him. He went, holy shit. And they graduated me. So I felt pretty good about that. Yeah. This is short, just a couple of mathematical formulas showing that, you know, we calculate this constant, have it align with the measurable observations we have, and that constant happens to coincide exactly with matter, antimatter appearance and destruction across the universe. So there you go. Okay. Where was I? This is all asking about gravity around black hole. So a black hole is a super duper concentrated gravitational hole, and there's not enough space around it to have any dark energy even be noticeable because of that 10 to the negative 80th constant. It's just so tiny that, you know, the vacuum of space really won't make a difference on that scale. John Doe, pretty amazing that brokers took everybody's money, then removed the ticker symbol. This is like FTX type business. Are we going to get a lawyer? I mean, eventually we'll probably have to do, if the Florida court doesn't go our way, there probably will be class actions. Right now it's kind of a wait and see to see what the Florida court does, because I think it's a better option to try to stop them in the middle of their crime than to try to get reparations after the fact. Make sense? Because they'll draw it out for 15, 16 years and they will refuse to settle. There'll be no cash. You can't sue for monetary damages, so you won't be able to get any cash out of it, but it'll be expensive as hell. And by then, you know, next bridge may have sold off. There may be, like, the legacy involved might be so antiquated and such a pain in the ass that no one has the stomach to do any of it. So, looking for the immediacy of an injunctive relief is the smart call. That's what Rose is doing, and more power to her, man. But yeah, it's not any different than FTX. FTX sold Bitcoin that doesn't exist. That's fraud. These guys sold us shares in MMTLP that don't exist. That's fraud. But it happens to be fraud that has a nice little loophole to it and a bunch of regulators who don't do anything about it. So it's fraud that's gotten the nod. Like, hey, I'm going to commit fraud. And the SEC goes, all right. that's where we are. They said it's okay. They can throw that curveball all day long, and we swing and miss it.